Good morning. Welcome to the seventh video on Introduction to Physics and for Neural Network. In this video, we will solve Burgos equation using finite difference. First, we shall briefly see what is finite difference method, and we shall also see what's the finite volume method. Then we shall solve Burgos equation using those methods. So these methods are very common methods in numerical analysis to solve any partial differential equations. First, we shall see what is finite difference method. The finite difference Taylor series. So you know the Taylor series is a series like this. So let's say we have a function f of x. So let's say we want to interpolate that by a value x plus h, then it will be like this: f of x plus h into first derivative plus h square divided by 2 factorial into second derivative and higher order terms. This is how we write the Taylor series. Based on that, we can convert that partial or ordinary differential equation into algebraic equations. So, in partial differential equation, we have these terms: first derivative, second derivative, and those terms. So, those terms can be represented in difference form like this. So this is a typical. So if you eliminate this f dash and those things, it's just an algebraic equation. So algebraic equation relatively easy to solve. That's why we use finite difference method. So in finite difference, we divide the domain into small grid points and we solve it over the grid points. Now you may have a question: why we need grid points? Why can't we solve the equation over the whole domain? The problem is, let's say we have a very complex solution like this. It's very difficult to know the nature of the curve. So if you make it very small, at least locally we can see the function is linear or quadratic. Or we can approximate the local variation as a linear and quadratic and ensure that the function satisfies the partial differential equation. That's why we split that domain into small grid points. So here we can say it's more or less linear. Then from here to here we can say more or less linear like that. So still we can preserve the overall structure of the solution. Anyway, that's not precise. That's why we call. So if we use those Taylor series and we can derive the first order derivative using this one. This we call as forward difference, and this we call backward difference. This we call center difference. So this is second order accurate, this is first order accurate, this is sort of first order accurate. Similarly, if we take more terms, we can derive higher order equations. So now we shall go to what is finite volume method. So finite volume methods are generally derived from integral form of the conservative equation. We shall briefly see what is integral form of conservative equation soon. So we shall see what is finite volume method. The finite volume method is based on integral form of conservative equation. So there is some advantage over finite difference when we solve fluid dynamics problem. So where we expect conservation. So here we will divide the domain into small control volumes. So, in previous procedure, we saw, so let's say we have a domain like this, we will divide it into grids like this. In fact, finite volume method also we can call this as a control volume, but it has relatively slightly bigger advantage. So in finite difference method, we should ensure that our grids are rectangle. So of course, we can convert that into some complex grids through transformation. But basic finite differences can only handle this kind of rectangle or square grid. But finite volume can able to handle grids of any shape. So of course we can't make any arbitrary shape kind of grid. For example, these skewed grids are not allowed. So this is not within the scope of this lecture, just we can maybe for the time check, you can assume that we can make any grid, but in practice we can't use any kind of grid. We should avoid these kind of grids. So this we call as very skewed grids. So now we shall see what is integral form. So in this video we will derive the integral form from the differential form. Please check the video by Professor Suman Chakravarti of IIT Kharagpur. So on fluid dynamics lectures, where he derived these equations from the Reynolds transport theorem. So that's the best way of deriving the integral form of conservative equation. For the time check, just to show what's the difference between integral, here I have shown how to derive that from integral form, so differential form. So this is a standard form of writing governing equation fluid dynamics in differential form. If we integrate over the control volume, we will be getting this one. So this we got after applying Gauss divergence theorem. So basically this term can be represented as F into N into Ts. For example, let's say we have a quantity like the flux at this point or at this phase. This is F and this is a normal vector. This is N and this is length. For one dimensional or sorry, two dimensional, this is length. For three dimensional, this is surface area. So that's what we have written here. So this integral can be written as summation. So let's say we have a control volume like that. All the fluxes coming in and out is equal to the net change in the conserved quality. So that's why we can ensure we can say finite volume always ensure conservativeness of flux. So that's what we have written here. So just we have converted that into integral into summation, and AF is a area normal. So one of the biggest difference between finite volume and finite difference is in finite volume, we calculate that flux using a Riemann solvers. So for example, let's say we have a phase, we have a cell like this, we have a cell like this. So this is I and this is I minus 1, this is the phase of the cell. So what we do is to calculate that I minus half, we will make one interpolation from this side and this side. So if it is a first order, we will assign this I minus this right side is equal to II. That is maybe UR is equal to UI. UL is equal to UI minus 1. This we call as the first order flux calculation. So basically this side and this side, we are just interpolating or just assigning, not interpolating, just assigning. And we have two fluxes at the phase. So what we can do is we can take average of those fluxes and assign it at this point. So this we call as a center, just average flux. Basically this average flux won't work for advection dominated problem. In that case, we should use some Riemann solvers. So Riemann solvers, there are plenty of Riemann solvers available. Very basic one is Goodenough flux. So you can also check Rosanov, Lax-Fetish, Rho flux, HLSC, AISM, and those families. So that's a very big area. Now we shall briefly see the summary of what is finite volume method. So in finite volume method, first we should divide the domain into small cells. Then we should apply that governing equation locally on that every cell. So let's say we have a cell like this. First we should calculate centroid of the cell. We should also calculate that edge length, then normals. Once we calculate the normal, we should calculate fluxes on every cells. Then we should multiply that fluxes with the area in 2 dimension or length in, area in 3 dimension and length in 2 dimension. and we should also multiply that with normal of the flux. So then we will march over time. Summate all the fluxes, then we march over time. This is how the finite volume method works. Slightly more complicated than finite difference method, and slightly less easier than the finite element methods. I hope you got an overall idea how finite volume method works. And now we shall make it a little bit more precise. So let's say we want to apply on one-dimensional equation. So in this presentation, we will see only one-dimensional equation. So this is how we have to integrate that over the control volume. So our control volume limit is x minus del x 0.5. So this is I, and this is xi plus h by 2 or del x by 2. This is x minus h by 2. So I'm just assuming del x is equal to h. So that's why we have taken this limit and integrating that to 0. So if you do that, this term we will be getting average at this term, and here we will be getting those value because here the average is, so here the normal is I, here the normal is minus I. So this will become f this side positive, this side negative. That's why we are getting this one in loop. So this del x will come here, and if we divide everything by del x, we will be getting del x at the denominator. So it's a very straightforward derivation. That's why we are getting this one. This we call as a conservative discretization. So based on how we calculate the fluxes, we can achieve first order, higher order, or any order of accurate schemes. If you want to know how to achieve higher order accuracy in finite volume method, please drop one comment. I shall make one separate video for that. So our central scheme is looks similar to that fi minus 1, sorry fi plus 1 minus fi minus 1 divided by 2h. But here just we are, instead of I plus 1 we have taken I plus half and I minus half and divided by h. So both are equivalent. So this is also central schemes. So we already know advection equation has some issue when we use central difference schemes. So we should give some way of operating to this finite volume method. Then only we can able to handle any fluid dynamics problem. Anyway, at least simple fluid dynamics problems can be handled using central plus small d equation because most of the fluid dynamics has inherent viscosity. But moment we go for high Reynolds number, this scheme cannot be stabilized. In that case, we have to give we should add either upwinding to the solver or we should add some artificial viscosity. So that is added by these Riemann solvers, the Godunov schemes. So let's say we have a problem like this. So this we call as the Riemann problem. So basically this problem will be having discontinuous initial conditions. And if we have like this one, if L is greater than F1, so this is that is this case, this is shock. If this is the case, this we call as a rarefaction. Actual rarefaction cannot be like this, but we can call as a rarefaction shock. But in physically, there is no rarefaction shocks. So in this case, we should choose fluxes like this. If we have the rarefaction, we should calculate flux level. So this procedure ensure proper upwinding. If it is like that, so the wave will be moving in this direction. So if we calculate that this will become a bias tensor towards this direction. That is I minus 1 and I. So now we shall see the difference between finite difference method and finite volume method. The finite difference method uses the differential form of governing equation, but finite volume method uses the integral form of governing equation. And here we use grid points, but in finite volume methods we use control volumes or cell. Here variables are defined at the grid points, but in finite volume method what we do is, so let's say we have a cell. We already saw we calculate this fluxes across these cells. Then finally, what we do is we will calculate the primitive variables or any variables at the cell center or centroid. So in that, in other words, we can say we calculate uh, cell average data, because on the right hand side we have a cell average data in the finite volume method. So what I have shown was, maybe let's go to the slide. Here you can notice that we have this one. This U bar is cell average. This U is EU. But if we do an integration, we will get a cell average data on the over the cell. So now we shall go to our code. So in this code, before that we shall see what is conservative non-conservative governing equation. So this is a non-conservative form of Burgers equation. Basically, Burgers equation, we don't have this viscosity. If we have a viscosity, we call as a viscous Burgers equation. But without the viscosity, it's very difficult to solve the Burgers equation. That's why we have considered viscous Burgers equation. In our code implementation, we will be having this viscosity, but that viscosity we call as a artificial viscosity. We shall see whether we can solve the problem with or without this artificial viscous term. So in this term, you can notice that the u is sitting outside of the derivative. But here you can notice that u is inside the derivative. So if we can able to write this thing in terms of divergence form, so basically this term we can represent divergence of u square. So then we can call this is a conservative scheme. If you are unable to write this in divergence form, we cannot call that scheme as in conservative form. Lot of equation cannot be written in this form. In that case, we use some sophisticated treatment to do that, solve the problems. So here this f of x is u square by 2. So this is called a convective flux in Burgers equation. For different for Euler equation, we'll be having different flux term. For dam break problems, we will be having different flux terms. So now we shall see how to solve this problem using FDM. So here we have taken center difference scheme, but it's always good to use upwind schemes because we have added the artificial viscous term here. It can stabilize both upwinding and downwind. But the value of the viscosity plays an important role. So in addition to that, we can also write this as a half, and we call it the finite difference that we call as a conservative finite difference method. So if we write this P or this FD, the finite difference method can also capture shocks better than the schemes. Anyway, we shall explore that in our code. Now we shall to come to finite volume method. So in finite volume method, as we already saw, there are certain flux equation will be like this. The flux equation will be like this. So now you may have a doubt. So in Vestek Mallashegra book, the Introduction to Finite Volume Method, they would talk about Riemann solvers and this way of stating. But still we call it a finite volume method. What's the difference between this and that? Actually, that is a case of this method of finite volume method. The only difference is, as I already told, so in those methods that F5 plus 0.5 is evaluated using Musser scheme. MUSCF. So this will provide upwinding to the solver so that finite volume method can be able to solve the advection dominated problem. So here to calculate Fi plus 0.5, we can use muscle. Then the resultant of the muscle will be fed to Riemann solver to give any flux. Then we will substitute here to solve it. This is how we solve high speed flows. In low speed flows, we no need Riemann solver. We can use a cell average of left and right side to calculate flux. So that's the difference between the high speed finite volume methods and the low speed finite volume. Anyway, I have just explained the overview of that. If you want a detailed explanation of high speed finite volume method or compressible finite volume method and incompressible finite volume method like simple piezo, please drop one comment. I shall make one video so that you won't get confused between that incompressible finite volume method and compressible finite volume method. So, as a thumb rule, you can say the incompressible finite method what we have seen is a subcase of high speed flow finite volume method. But after that, we have some projection and those things that is like different from the high speed compressible base method because piezo are simple and those kind of algorithm are not robust to handle high speed flows. There we use some different way of solving, but in low speed flows, we use projection based algorithms like piezo simple so that we can decouple and solve the algorithms. So now you may have a question. We know the finite volume methods are integral formulation and finite element method use a weak form which reduce the derivative requirement by one. So are they able to handle shock because they reduce the derivative requirement? Is it the right statement? Because I have seen a lot of a lot of this kind of statement in lecture notes or even review comments. The finite volume is best to handle shock. Finite difference is not good to handle shock. That's because finite volume works on integral formulation. But I am not convinced in the topic. I will give an explanation why I feel that is not a right way of interpreting. So we know in finite volume method we do an integral form. I mean, right now we shall concentrate about finite element method. So in finite element method, what we do is, let's say we have a governing equation, we will multiply that with a shape function and we will integrate by parts. Once we do it, you'll be getting this form. So this derivative in u is shifted to v. Here also is like that. And we have the boundary terms. This is how the finite element method works. You can notice that there is no requirement of the derivative of u because we have discontinuous of flux and conservative property when we are solving problem having shock. But here we are not explicitly calculating. But the problem is this phi itself a solution of u, linear combination of psi phi will give the solution of u. In other terms, if we calculate derivative here, the derivative also come here. So we are not escaping from derivative whether we solve finite difference or finite volume. But indirectly, maybe visually it look like that, but in other way we be calculating derivative. In addition to that, finite volume method cannot directly, especially the finite element methods like Galerkin methods, cannot handle shocks without any special treatment. So we may go for Stig function up to Petro-Galerkin schemes or discontinuous Galerkin schemes. So even this discontinuous Galerkin scheme, it's a hybrid of finite volume method, FVM, sorry, FVM and Galerkin finite element methods. Because finite element methods give the central schemes like standard FPM, then we should provide some occulting that is provided to flux calculation in DG methods. If you want a tutorial on how this SUPG works, how the finite element methods can able to handle advection dominator problem, please drop one comment. I shall make one separate video for that. So in terms of finite volume method, because we are doing integral formulation, we are escaping from the derivative calculation. But visually it looks like that. But if you have a close look at this formulation, this is closer to finite difference derivative calculation. So we have a this formulation does not explicitly calculate derivative through mathematics, but in numerics we are calculating the derivative. Anyway, in problem having shocks, directly or indirectly, we will be calculating derivative across the shocks. But we use some special treatments like viscosity. For example, let's say we have a shock like this. If we add the dissipation terms, so that is mu into dou square u by dou x square, this will smooth the shocks. So instead of calculate, if we calculate derivative here, this will give a infinite value. But if we calculate derivative across the smoothened shock, we will be having some finite value, so that our solution won't blow up. So these concepts, so this smearing of the shocks can happen because of biased schemes or upwind scheme, or we add some explicit viscosity to stabilize the solver. Anyway, in the code we shall see how we can stabilize these solvers. Now we shall go to the code. First we shall go with standard finite difference method. Here we have used define the number of grid points and CFL number, flow time, etc. And this is the viscosity we have provided. So here maybe we will be calculate the dt based on two parameters. One is CFL number, another one is diffusion number. So CFL number is CFL is a non-dimensional number which defines the stability of the flow, which is calculated by C into del T divided by del X. So for most of the problem, it's good to use CFL number less than 1. But if we use a higher order methods, we can push the limit to beyond this value. So diffusion number is generally written like this. So diffusion coefficient nu into del T by del X square. So this is a diffusion number. So based on this value, we should design the del T. Yes, solution will blow up. So that's what we are calculating it. We are calculating the minimum del T which stabilizes both the convective part as well as diffusive part. Then these are just plotting stuffs. So here we are using central difference scheme to calculate the derivative. Here we are providing upwinding because upwinding is a little more stable than that. Now we shall run our code. Upwinding means ui minus ui minus 1 if that is a right moving wave. If it is left moving wave, we use the stencil ui plus 1. So if the move is left moving. If it is right moving, we should use a stencil ui minus 1. Otherwise, our scheme may become unstable. So it has completed the solution. Now we shall see the animation. So you can notice that it can able to stabilize a solver. Now we shall go with central scheme. So in central schemes, just to calculate the derivative, we have used the central. So here. So this ensure this is central derivative. So what it does is it will calculate ui plus 1 minus ui minus 1 divided by 2 delta x. So now we shall run this without viscosity. We already saw without viscosity, this will give unphysical results. We shall change that to 0 and we shall run it. You can notice that the solution is unstable. So because of lack of viscosity. Now we shall add some viscosity to this solver and we shall run it. Basically viscosity, what I am saying is, so our governing equation, the Burgos equation will be like this. So this is a Burgos equation. So here we will add some extra viscous term. Then nu into dou square u by dou x square. So this term is this one. So now I hope we may able to get some solution. So still is oscillatory. We will explain that. Then we shall tune it. So at least it's not that much bad like previous one because this is not optimal. Maybe we shall reduce it for increase it for the error need. Now oscillation is slightly reduced. You can notice that there is no big oscillation. Even this is not enough. We may add a little bit more. So right now we are adding too much viscosity. That's creating some issues. So adding too much viscosity also not good. So we should add one optimal viscosity based on the problem. So please note this issue. This is one of the problem in CFDs. So finding an optimal viscosity is very difficult when we have problem having shocks. Of course, we have decades of solvers. They give some optimal viscosity for variety of the flows. Still, it's not stabilized. No, it's fine. But you can notice that solution is very dissipating. So when we add some viscosity, even if you use occulting, this is also for this problem the solution is dissipating. So another one is a Goodenough scheme, that is a finite volume based scheme. So where we use the flux calculation, we decide the occulting based on the flux. So that's what we have given here. Please check the formula. If we have a shock, we will calculate the average of that left and right training characteristics or speed. I'll being say characteristic. The shock speed is calculated in left and right state average of it. If there are rarefaction or other phenomena, we either go for left value of flux or right value of flux. If you want a detailed explanation how this Goodenough scheme work, how we design a high-speed Riemann solvers of those things, please drop one comment. I shall make one video. So that's a very advanced topics. That's the core of high-speed fluid dynamics. If you want to solve any supersonic or hypersonic flow, these are the things we should care when we design one solver. And most of the solvers like HLSC scheme, ASM schemes takes care of in slightly different way. So this is a Goodenough schemes. So those are some refined version of the Goodenough schemes. Even if you use Goodenough schemes, we will get snared shocks in this problem. So because we have used the first order schemes for reconstruction. So we already told to calculate that cell interface value F5 plus 0.5 and F minus 0.5, we should use higher order schemes to get a better shocks. Some of the higher order schemes for this problem having shocks are muscle. So this muscle is slightly different from the muscle what we learn in low speed flows. Here we use limiters that I call muscle. Anyway, limiter is there we have limiters like min mode, super B, those kind of stuff. Other way to achieve higher the scheme is Vino, weighted essentially non-oscillatory schemes. When we use Vino or muscle, we may get a better shock resolution compared to these first order schemes. So those schemes we call as the higher order schemes. So this is what we got. So anyway, here also the solution is very dissipated. So I hope you enjoyed the today's video. If you have any queries, please drop in the comment section. So thank you for watching.